All right, so today we are going to talk about chapter 3, that is orthogonal expansion. So the homework problem for these sections are for 3.1 is number 1. For 3.2 is number 2, number 4, and number 13. And for 3.3 is number 4, 5, and 6. And they are due together with the homework problem for 2.7. They are due on April 8. And okay, so the first section is Fourier's method. Fourier's method. Joseph Fourier is a very interesting person. In 18th, he was a French mathematician in the 18th century to 1768 to 1830. He has very interest in biography. So let's just look at. You can check his wiki site. So if you check his wiki site, so I can probably make this. Okay, this and then let's look at it. And he was actually at the time of Napoleon. So he was appointed by Napoleon as a governor of Grenoble, and then there's Joseph Fourier Institute in Grenoble under his name. Anyway, so what we are going to talk about here is actually his contribution in heat conduction. The way he studied heat conduction is quite very original, and it has a fundamental impact in mathematical analysis. So let's recall the heat equation. So this heat equation is a constant c squared times k times uxx, but we assume this constant is 1. So we have this simplified version of heat equation. We assume that x is from 0 to pi and t is positive, and the initial condition is at u. The boundary condition is u0t and u pi t equals to 0, and the initial condition is when t equals to 0 is fx. So that is a heat equation with this boundary value and then this initial value conditions. Now, so that physically it means that you have a rod from 0 to pi, and you assume that the initial temperature at the end point, the temperature is O0, and the boundary, and then the initial temperature is given by this graph fx. That's initial temperature, and you want to find the temperature at time t and at any position. So that is the problem. Now, if this interval is from is negative infinity to positive infinity, then we know how to solve this using the Green's function or the heat kernel, and then we can express the solution in terms of the initial condition. We solved this before, and even if the interval is infinite from 0 to infinity, we can still solve the equation using the reflection method. But here, the difficulty is that we have a finite interval, and we assume that the temperature at the endpoints are 0. So let's see. So Fourier is the first person who came up with the method to solve this problem. Let's see how he did it. So he assumed that, okay, let's say u is a function of xt. Let's try to find a solution where this variable, this function can be separated into two, as a product of two functions. So this method is we usually refer as separation of variables. So now we plug this in back into this equation, and remember when we find the partial derivative with respect to t, we only involve this term. So on the left hand side we have t prime. This, okay, let me erase this. We have x and t. On the right hand side, we find the partial derivative with respect to x. That means that we involve only this term. So we have x prime prime, x, and t. Now, if we divide both sides of this by capital X times capital T, little t, so then the left hand side becomes t prime t over dt equals to x prime prime x over xx. Now that is the equation. That is what we get after we divide both sides of this by capital X and capital T. Now notice that this left hand side here depends only on t, but this right hand side here depends only on x. Now, when you have a function that depends on the left hand side depends only on t, the right hand side depends only on x, what you can say is that this expression here must be a constant. So we will call this constant as negative lambda. Okay, let me, instead of calling it negative lambda, let me call it as negative constant c. Now, then we want to solve this equation. Let's look at this equation first. Then this is x prime prime equals to negative cx, and then we move everything to the left hand side. And this is, now this is a second order ODE with constant coefficients, and the characteristic equations is this. So therefore lambda equals to positive square root of negative ci is a complex root. We assume c is positive. Then that would mean that the solution, the general solution of x is c1 cosine square root of cx plus c2 cosine square root of cx. Now we now come back to look at the solution that would also satisfy these boundary conditions. Now the boundary conditions is u x 0 t, which is x 0 dt equals to 0, and u pi t equals to x pi dt equals to 0. Now, this is a function, and then this must be identically 0. That would mean that both these two terms must be 0. So therefore, we need to find a solution x so that it satisfies these two boundary conditions. Now, if we plug x equals to 0 into this expression, then we know that we C1 cosine 0 plus C2 sine 0, which equals to C1. This must equal to 0. So that would mean that the x, actually, this constant here is 0. So we have only this term left. Apparently I misspoke. This should be this is not be sine cosine. It should be science here. So therefore we have that this x is C2 sine square root of cx must. Now we also need to satisfy this second boundary condition. So pi here, so that means C2 sine square root of cx when x equals to pi, this equals to 0. Now sine of something equals to 0, that means that this something here must be an integer times pi. So therefore square root of c is n. So therefore c is actually n squared. We actually will come back to this kind of separation of variable in the next chapter, but here just give you the preview of Fourier's method. Now we have c equals to lambda squared, so x, I would just forget about the constant, would be just sine square root of c, sine square root of c, so that would be n x. Now if we come back to this equation, now c equals to n squared, so therefore this, we look at the equation involving t, so that what we have here is I can make it smaller. So this would be t pi t equals to negative n squared. So I'm coming back to this equation here. So now we know that this is t prime equals to negative n squared t, and this is an equation we have been we know how to solve it, and then the solution is is e negative n squared t. This is now, so therefore we find a solution xt, one solution for any n. We find a solution that is in this form, sine n x, where n we can when n is 0, so that this would be 0. This term would be 0. So we actually run it for 1 to infinity. All of these are solutions for any n, but we not only need to find a solution that will satisfy this boundary condition, but we also need to it also need to satisfy this initial condition. Now, to do that, Fourier's idea is that, okay, each of these would be a solution, so the linear combination of these an e negative n squared t would also be a solution. For a finite sum, it would also be a solution. But what is interesting is that he actually have an infinite sum, would also be a solution as well. And this is also a solution, but then we need to find a solution in this form that would satisfy the boundary, the initial condition as well. So the initial condition is when t equals to 0, this equals to fx. Now, when t equals to 0, I put t equals to 0 here. So this term would give me 1. This term would give me 1. And then we would have n equals to 1 infinity an cyan nx. So the idea is then we need to, in order to find a solution, we need to determine this an. But how do you determine this an? So this is the key point here. The right-hand side is a trig function. It's a sum of trig functions. But left-hand side is an arbitrary function. So of course, we have more functions than a trig function, like the exponential function. You would never be able to express an exponential function as a finite sum of a trig function. The ingenious idea of Fourier is that, okay, for any arbitrary function, satisfy some condition, which we are going to talk about later, you can express this fx as an infinite sum of the trig functions, and this infinite series is what we call as the Fourier science series. And this is how we and the idea is that now we need to determine this an. If we are given an f, how do you determine this an? And now to determine this an, we modify both sides by cyan mx. M is any integer, fixed integer. Then I modify this to both sides, and I have this an cyan mx cyan nx. Now, then I integrate both sides by from 0 to pi. So assume that I can interchange the integral sign with the summation sign, then I would have this. This actually, the interchange of the integral sign and infinite summation sign actually requires some justification, but Fourier did not care about that at the time. So he just assumed that you can always do that. So then you would have this dx. Now, how do you evaluate this integral? To evaluate this integral, we use this formula, the trig identity, that tells us that cyan a cyan b equals to 1/2 of cosine a minus b minus cosine a plus b. Okay, you can go back to, we actually learned about this in Cal 2 as well, but you can go back to your trig identities, and then you will find that this is the trig identities. So, I mean, you can verify this easily. This is cosine A, cosine B, plus cosine, plus sine. Plus sine A, sine B, and this term is cosine A, cosine B, minus sine A, sine B. So if you minus these two terms, then this term would cancel, and then you have 2 of this term. So that is where you get this term. Okay, so that is some trig identities. Now, we use these trig identities, and then we evaluate this integral sine mx sine nx dx. So this is my A, this is my B. So then I use this trig identity, so I get the integral. I'm going too fast. The integral here actually is from 0 to pi, not from 0 to infinity. So that is the integral from 0 to pi. This is cosine a minus b, so it's m minus n x minus cosine m plus n x dx. Now, the antiderivative of cosine, of course, is sine m minus n x n minus n, and this is sine m plus n x m plus n, and then this x is from 0 to pi. Of course, sine of an integer times pi and sine and at 0 are all 0, so this term is always 0. Except that here we have to assume that n is not m, because when n is m, this term would be 0. So what we did here would be illegitimate. Okay, now what happened when n equals to m? When n equals to m, then this integral here becomes sine square of nx, because these two terms now are the same. And then how to evaluate this? Then you use the fact that this actually equals to 1 minus cosine 2nx over 2. So you this I mean the and then you look at the antiderivative, and then this integral is 1/2. Let me write here 1/2 x minus sine 2nx over 2n, and x get from 0 to pi. So you plug this back here. This again would get to 0, so you have pi/2. So, all right, let's we now evaluate these integrals. Now, so we come back to this expression that we have here. We know that this is, let me use the red. This term, when n is not m, that all these terms would be 0. When n is would be 0. When n is m, this term would be pi/2. So in this, although this is an infinite sum, all the terms would be 0 when n is not m. N is not this fixed m. So, therefore, the only term that you have left is am, and then when n is m, this integral is pi/2. Then from here, you know that an is 2 pi, the integral from 0 to pi of fx sine mx dx. So this. All right. Now so let's summarize what we did. So that is a Fourier's method here. So we want to solve this heat equation on the interval from 0 to pi, and then the initial condition, the boundary condition is the temperature at the endpoints are all 0, and the initial condition is given by initial temperature is fx. Fourier says that the solution can be written as uxt as an, e negative n squared t sine nx, where n runs from 1 to infinity. And these coefficients here is determined by the initial condition, because fx here is ux. When t is 0, this term is 1. When t is 0, this term is 1. So therefore, you get n from 1 to infinity, an sine nx. Now, this an is given. Those are this is the Fourier science series of fx over the interval from 0 to pi. And this an is given by this formula from 0 to pi fx sine nx dx. So that is the this is the Fourier's method in solving this heat equation. We are going to come back to this method again in the next chapter, but this is just a preview to this to the Fourier's method, and we are going to continue to talk about the idea and the theory behind this Fourier science series. Okay, so this